Okay, I'm Stephen Su. I work. My English a little bit, not very good, so you have to bear with my accent. Uh, okay, I'm the test engineer, testing from very beginning, OCAD, that's pre-tape out testing, and the manufacturer testing, and the chip research and diagnostic testing, everything. But most of the test is based on very, very simple strategy. Oh, each core, each CPU has 64 words of BIOS and the RAM, and each one consists of one CPU has 32 opcodes. And they do have some registers. Each one have 8 registers, and they have a common port, communication ports with a neighbor, a run cell, and they have a stack, and they have some of them have special function like AD and some serial, some SerDes, different type of serial. And our latest chip is 144 core, where it's 8 by 18 array. We already saw that in Charlie's subshin. And the ROM, BIOS, boot, and mass function are in the positions. Okay. The most important, we know they have 262 communication port, and these all need to be tested. So the coverage, the strategy of the coverage is to cover some I/O pins, most of the I/O pins, most of the registers, 2 main stack, actually only 2 of each, all the RAM cell, each bit, and all the communication port, and all 144 nodes. But I have to emphasize again, I'm only doing the functional tests only. This chip is different from the chip in the conventional style. So, and my job is only testing the function. It's an I/O boot, a ROM BIOS, I'm not going to confirm them, and all the AD, SerDes, they are not included. My strategy is starting from the single node, then doing some neighbor parallel probe communication and the multiple node chain with self-migratory or migration test module. That's used to be called crawlers. I have about 4 or 5 type of test module. And some of the special opcode need to be tested separately. Also, I need to confirm different voltage at the 4 corners. Our chip has the design as one module with flip and flip. So one chip making into all 144 chip. And some of them added special function. So we need to test all 4 different orientations. Single node tests starting from the I/O is IOCS. And IOCS, just like Jeff showed you, we put some number into B register. B register is pointed to IOCS, and you raise the pin up and down. And the method I did is to write it to the pad and read it back to see if it is stable or it's not. And all the pin, I/O pin can be done like this. If you have a 4 pin like SPI, you need to write some different numbers. Also the same with all the register. The registers, since the register has 18 bits, I need to design 8 different patterns with bit flipping, like 0 and 3FFFF and 1555 and 2AAA, something like, keep flipping that to verify if the data is consistent. Also the same with the stack. And stack has a special function Jeff mentioned. The bottom 8 cells of the stack, they are keep recycling. We have to confirm that too. Each CPU has 64 words memory, each bit. So I'm using the same flipping pattern to test the all the cell. Writing the cell with a specific pattern, read it back, and to see if it is the same. A couple special opcode, and we need to design a specific test for that. And especially, we have micronext. Jeff showed you the micronext, and micronext, the location of micronext causing a different timing change. So we need to carefully test it, what's before the micronext and what slot micronext sit in. And I test, the four-corner test with a RAM pattern test. That's different saturation, different voltage, writing into all the 64 cells and read it back to see if they are all the same. There are two types of port test, multi-node port test. The first one is very short parallel programming. There are four nodes in a group like this. Starting with sending a command, have this node doing something, and then transfer here to have this node doing something and have this node doing something. And after this node completed its task, it will prepare the data and knock on the door. But at this time, this one is still working with this two. So we have to be sure the data is waiting and we can get it. So after the first step, second step, third step, knock on the door, giving the order or giving the data, and then collect the data in a sequence to see this data all comes back. This is very simple, very only one-step test. But we know it's 4-node simulation. It's still a little bit longer. We cannot do a very long test. This 4-node group were tested on all the I/O nodes. If the center node has the I/O connection with outside, it needs to be tested like this. And the last one I'd like to introduce is self-migration test module. This is the crawler, and it's a combined application test. It's also confirm the connectivity, all the port test. It's not only testing the communication, it also writing all 64 cells of the RAM memory, and then jump into it and then run it again and again. And the very, very simple one is a fixed path self-migration test. It carries a small program going through a fixed path and having all the node doing something, or leave that program, have the node keep doing something, and we can detect it if this node alive or not. And the second one is so-called random self-migration test. You just randomly go there, and it will go through using a pseudo random number to go through whole chips and all the 144 nodes, and they keep testing, keep doing something. And the last one is combine these tests. It not only go through the random pass, it also, before it go into the next node, it tests the forward node's integrity, everything, stack, register, and RAM cell. The testing its tester is sending one specific random number. This random number is keep changing, to neighbor, and ask neighbor to store it and to duplicate it into all the stack, and then store this same number to all the RAM cell, and then read them back, and then compare to the copy in the tester to see if it is the same. It should be the same, but it's hard to say. Sometimes it will if you bound into some really problem, some bits will change 2 times. Change to 0 and change back to 1, and then you never know. But it's very rare. But so we have I have this self-migratory testing module. They randomly test and keep testing, never stopping. Any problem, this module stop, and you don't see any toggling from any of the peripheral nodes. And this self-migratory test module can be used in the real chip test. And not only carry the test, but they can also set a specific path for the next program to come in, a bigger program to come in to do the test. For 144 nodes, due to the simulation, it's very, very time consuming. I set the 10 picosecond for 1 tick. For 2 node, like this one, transfer all 64 node forward over and have it to check it, then comes back, take, what's that? 180,000 ticks. And in the real simulation, it's about 40 minutes. But if we double the nodes, the time double. And every time you increase 1 node, you double the time. So the 4-node chain test will take about more than 3 or 4 hours. So this is a big node, and it's very difficult to test the whole chain in the most modern laptop. Yes. Oh, yes.
If you simulate twice as many nodes, the simulation runs twice as slow. So when he's simulating a lot of nodes, it's a very slow process.
Okay, this is the timing is only concerned about simulation, but for the real chip, the test module take about 1 microsecond to send itself crossover, but you take another 1 microsecond to do the test. So if you have a very complicated test, it's about 2 microseconds to go across 1 node. This is a diagram for the 144 node testing. It's actually I was using more than 16 threads. I automate the test procedure. I have the OCAD, the color force, running, start using DOS batch file, and at the end of my test, the program will exit and start the next test. So that's why we can facilitate this test, and we do this now more than about 150 or 200 tests in about 1 week. Okay, this is test preparation. The most important thing is using the automation to write a text file and port it into the OCAD. Since I have 150, 40, or 50 tests, I cannot just type 1 by 1. I need a utility to port it into the test. And before the test, I need to verify all the test environment is the same. And I need to set the logging system and I need to set the exit system too. This is a part of test program. It's one program divided into the 4 slides. It's for 4 different blocks. Each block has to be rewritten, like setting environment, setting test node, setting test program, and setting then loading the test program to specific node. This is the logging system. We can see in the beginning, at the starting, we know all the registers in stack, and then they start to run, and this is at the end. We'll see all the register data here and the ticks, and you can compare the ticks with the previous version and the similar program to see if this program runs well or not. And even you can just text compare to the previous log file to see if they are matched or not. This is a special condition, okay. For the micronext, like you test the micronext before with a no-op or without no-op or with literal loading function. This is the latest chip we did, for the comparison. And for some program, I can compare it with our S40 chips. Approximately the same, very close ticks from special test. And for the smart cell migratory test module, I have about 110, tests, and with some special condition. That's it.
Is that the traditional fireside? I'm not in an electronic mode. I am ready.